Yeah.
How many people do I have to thank?
Well, feel free to leave details out about me in order to make room for the other stuff.
Yours is, added a little bit more actually in there about your journals. And
Okay,
I thought
nice.
it would be important to say you publish in things like Proceedings of National Academy of Sciences, Nature, Climate Change, and Science.
That's nice.
Okay, I think we're going to need to take some seats here, including people who are standing there and not taking seats. So give it a minute for people to settle down. I see people walking. There's plenty of seats up here in the front for those of you in the back who aren't sitting. Okay, well, I think I may have succeeded in getting as many people sitting as I'm going to. My name is Dar Roberts, and I'm pleased to have the opportunity to introduce the second installment, the second keynote as part of the Wildfire Prevention and Policy Lecture Series. This presentation was enabled by generous donor support, and today is co-hosted with the Santa Barbara County Fire Safe Council. In particular, I'd also like to thank Direct Relief, providing us this wonderful venue to have this. It's very nice. Remind everybody that we do live in a time of COVID, and so if you want to wear a mask or feel most comfortable with us, please do so. Also a reminder that there will be a reception to follow. So once Park is done giving his talk, there's a reception, there will be food, and there will also be various tables out there. So one, for example, you might visit is the Fire Break Tequila Premium Anejo. So if you like tequila and you like fire breaks, that might work. And then finally, I'd like to introduce our speakers. So Park Williams is a professor in the Department of Geography at UCLA. He earned his PhD from UCSB in 2009, followed by postdocs at UCSB and Los Alamos National Laboratory. He became a research professor at the Lamont Doherty Earth Observatory starting in 2013, joining the Department of Geography at UCLA in 2021. He has co-authored or authored a number of very influential papers in journals such as the Proceedings of the National Academy of Sciences, Nature, Climate Change, and Science, and was recently featured in a story about long-term drought in California published in the Los Angeles Times. Park Williams is a hydroclimatologist whose research aims to understand the causes and consequences of hydrological streams such as drought. Questions that he finds especially interesting involve the effect of human-caused climate change on the hydrological cycle, ecological systems, and humanity through extreme events such as heat waves, wildfires, and flooding. We are pleased to have Professor Williams tell us more about how climate change is likely to impact California and how this has complicated our ability to plan for, manage, and develop wildfire policy. And with that, Park.
Thanks, Dar. Okay, thanks for having me. This thing is recording me, so I don't need to carry a mic as long as people can hear me. Okay, if there are people, if you're in the back and you can't, then I'll pick up the mic and try as best I can. So I took the train up this morning, and in Santa Barbara, there was just one more stop, Goleta. And in Santa Barbara, they encouraged everybody to get off the train there. They said, nothing is happening in Goleta. I thought this might be canceled. I'm so glad that I showed up. This has been a really great day. For those of you who missed it, there was a workshop this afternoon that was just fantastic with tons of expertise, especially on the local fire regime of coastal Santa Barbara County. Kind of an intimidating experience because this talk that I'll be giving is not about the local, it's about the large scale. And one of the reasons for that is because Fire is a difficult thing to study locally. It's a binary thing. There's either a fire or there's not. If we looked at the fire record, for example, in this spot right here, we just see a bunch of zeros for a really long time. And so if we want to know how climate is affecting fire at this place, we actually need to zoom out. And the bigger you zoom out, the more you can see the effect of climate on fire. The more you zoom in, the more you see the effect of people, land management, those types of things on fire. Fires, of course, on everybody's minds, especially in the last couple of years here in California, because they've been extraordinary. There are just a couple of maps of the areas that have burned in California let's see if this thing is on. Oh, the pointer doesn't work on the screen. The red areas are the areas that have burned just in the last 2 years. There have been some extraordinary fires. I was actually camping just in this area, the footprint of the Dixie fire, 2 weeks before it started, during that incredible heat wave of the summer of 2021. And those were right on the heels of some spectacular and dangerous fire activity that occurred in 2018. The numbers that have been coming from fires in the Western United States recently are mind-boggling. In the first half hour of this spread of the campfire, for example, the fire was consuming about 7 football fields per second. These big recent wildfire years have been part of a trend that's been going on for decades. If we look across the Western United States, the area that burns in a given year has increased by over 300% since the early to mid 1980s. The reason why this record and many other records I show today start in 1984 is because that's when our really precise satellite-based records of fire area begin. But this trend probably actually began in the early 1970s. California has better records that go back to the 1970s, and they show that, that this trend has been going on since the middle of the 1900s. And here, just zooming in on California, this is the satellite record of area burned in California. You can see that there was a trend before 2020 and 2021, but it's kind of hard to appreciate just how strong that trend is, because 2020 and 21 really own this graph now. I had to double the scale of this graph in order to accommodate those 2 years. But fire scientists were talking about this trend toward more fire in California before 2020 and 2021 blew the pants off of the previous records. Here's a paper I co-authored in 2019 about fire and the effect of climate change in California. And this record here is showing the area burned from 1972 through 2018 in California. When we see records like this, we tend to immediately think, oh, this is a bad thing. We don't like fire oftentimes, right? It burns our stuff, it burns us, or it puts smoke into our lungs that's unhealthy. But is it inherently a bad thing? Definitely not. Fire has been on the continents for as long as plants have been on the continents. And if you walk through any old-growth forests in California or the rest of the Western United States, you see signs of wildfire all over the place. Like here, a fire scar embedded in the trunk of a giant sequoia tree. And we can, as tree ring scientists, we can actually look back and detect old fire scars embedded within the tree ring records, and we can tell exactly when they occurred. I'll show in a little bit that fire across the Western United States was very regular until the late 1800s, early 1900s, and these fire scars are eliminated from the tree ring record. But fire is not perceived as a good thing by people who are living too close to it, and increasingly frequently we've seen people in harm's way because of fire, either immediately in harm's way because of flames, or much more often, or many more people are affected by the smoke that is emitted by fire and taken long distances. And after fire, the hydrology of the land can change. And I don't need to remind anybody here in Santa Barbara of just how damaging the post-fire mud flows can be. And even ecosystems, even though ecosystems have been dealing with fire for millions of years, even some ecosystems are suffering because of the gigantic and highly severe fires that have been occurring in the most recent decades. Here's an image from the Las Conchas fire footprint in the Jemez Mountains of northern New Mexico. I was living in northern New Mexico in 2011, and this fire occurred shortly after I moved to that area. And this is a ponderosa pine forest. Ponderosa pine trees don't drop their seeds, or they're not very good at spreading their seeds very long distances. They've always been dealing with fire, but historically, fire would come through every 5 to 15 years, and that would keep the understory pretty open. And there would be an occasional lucky old tree that was able to get up during a wet time and survive the subsequent fires, but fires wouldn't be all that severe. A fire like this that opens up many square kilometers of canopy by killing everything this is going to take a very long time for this tree species that's not very good at reestablishing long distances to reestablish. Very likely, if we revisit this site in a couple hundred years, we do not find ponderosa pine forest. So whether or not fire is good or bad is really a matter of perspective, but it's really clear in looking at our financial relationship with fire to see that we see fire as a bad thing. We react to fire by putting them out. And successfully, we put out well over 90% of all fires that are ignited, probably closer to 99%. And that, like I said, is documented in the tree ring record. This tree ring record here is a very typical one. We have tree ring records from thousands of trees across the western United States that have the precise years of fires recorded within them, and then the late 1800s, they just vanish. And the reason is because we, in the late 1800s, early 1900s, took control of wildfire in the western United States. We were very good at putting fires out. Fires started becoming less common first, probably because of grazing. We had lots of livestock going through forests and eating up grass. And then in the early 1900s, we got very aggressive with fire suppression across the western United States. So that spending graph that I just showed you shows that we are still fighting fire very hard. The bigger the fire year, the more we spend. So why have we lost control of fire in the western United States? Well, to answer that question, we're going to stay pretty broad and we'll just show you the record of area burned for two different land cover types in the West. Here on the left, we're looking at the annual area burned in forests, so forest fire. On the right, we're looking at the rest of the area burned in the western United States. And you can see that by far and away, the most dramatic increase in area burned has been in forested areas. Area burned has also been increasing in non-forested areas, but not as dramatically. In California, it's a similar story. Increases in both, but much more dramatically in forested areas. We'll understand why in just a little bit, but before we get to why, let's look at the seasonality. When are the increases occurring? The increases in the area burned, both in forested areas and non-forested areas, are dominated by summertime fire. At the end of this talk, I'll talk a bit about fall fire, because fall fire is the type of fire that here in Santa Barbara you're probably much more familiar with. But the fires that are really growing the most in the western United States are summertime fires, the dry season. And what types of fires are growing the most? Well, both in forested areas and non-forested areas, it's the biggest fires. This graph is showing you the magnitude of the burned area trend in 10 different classes of fire. The smallest fires on the left and the biggest fires on the right. The biggest fires in the 1980s are much, much smaller than the biggest fires of the 2010s and 2020s. So why is this? Well, to understand why the fire regime of the western United States is changing so quickly and so profoundly, it's important to first think about the three main pillars of fire. What are the three ingredients for fire? One is obviously fuels. So you need conditions to be wet enough to be able to grow fuels in order to have fire. But then you need conditions to be dry enough to dry the fuels out and make them flammable for when you have the inevitable ignition, either from lightning or from people. And then generally it helps to have some wind to spread the fire faster than people can keep up with it. We'll focus first on dryness. and the effect of dryness on fire. And the effect of dryness on fire is very, very obvious if we just do an analysis where we look at the area burned every year since 1984 versus this variable called the vapor pressure deficit. And the vapor pressure deficit is a variable that represents the combination of heat and humidity. It's really the aridity of the atmosphere, and you can think of it as the sponginess of the atmosphere. Every dot on this plot represents 1 year from 1984 through 2021. And on the vertical axis, we're looking at the amount of forested area that burned in any of those years. And on the horizontal axis, we're looking at the vapor pressure deficit. The fact that all these dots are on the same line indicates that there's a very strong relationship. The higher the vapor pressure deficit, meaning generally the warmer the atmosphere, then the more forest area burns. And this is a very reliable relationship. Surprisingly strong, given that humans are responsible for igniting most fires, and humans try and suppress essentially all fires. And there's so many other things that matter for fire, like wind. But at the end of the day, if you tell us what the vapor pressure deficit was in a given year, we can tell you with pretty high confidence how much area should have burned in the western United States forests. If you're looking carefully, you might see that on the vertical axis, the numbers are not going up in a linear fashion. They're going up exponentially. And that means this relationship that I'm showing you is actually an exponential relationship. The reason why I showed it first to you in this funny way on the left is to show just how stable that relationship is. The difference between the blue dots from the 1900s and the red dots from the 2000s is pretty clear. As it became drier over the last 40 years, we had more fire, and that relationship stayed constant over the last 40 years, despite so much chaos. But that relationship is actually exponential. And that means that as the atmosphere has warmed and dried, every little bit of warming has caused much more forest fire than the previous equal bit of warming. This is really important because if warming is going to continue, as we believe it will, then we might expect record-breaking years like 2020 and 2021 to once again look very small compared to the records that are potentially to come in the next 10, 20 years. And so here with these two plots alone, I'm making the case to you that the main reason why we've seen this very rapid increase in forest fire activity in the western United States is because of warming and drying of the atmosphere. In the next several minutes, I'll make the case that it's more complicated than that. But if all else is equal, climate is really playing a big role in the increase in forest fire activity in the western United States. But wildfire, like I said earlier, is affected by more than just the dryness, for example, fuels. And that should be pretty obvious just by comparing two very different ecosystems that live pretty close to each other. Here's a dense forest in the southern Sierra Nevada, and here's a much sparsely vegetated desert just 100 or 200 miles away. If you expose both of these places to a drought, and then expose both of them to a bunch of sparks, it should be pretty obvious that the one with more fuel is going to probably carry fire more easily. This ecosystem on the right, the desert ecosystem, is probably always or almost always dry enough to burn, but very often fuel availability is what limits this place's ability to have large fires. Whereas on the left, fuel is not a big limitation. Instead, the biggest limitation is this place on the left is oftentimes too wet to carry fires. It takes a big drought, but if you get a big drought and then you get a spark on a pretty windy, hot day, then you're very likely to have a pretty big fire. And so fuels, it makes sense that fuels must play a role in how fire in the western United States has been able to respond to climate change. And that's actually pretty clear if we go back to our scatter plot analysis. The plot on the left is the same one that I was showing you earlier. Warming and drying has led to this reliable, strong increase in forest area burned. If I do the same analysis for non-forested areas, then we see, okay, yes, the warmer and drier the atmosphere is, then the more likely you are to have a big fire year, but that relationship isn't nearly as strong because a bunch of other stuff matters too. For example, during the drought year, was there enough fuel in the really dry area to actually carry fire? Also, human populations are higher in non-forested areas than they are in forested areas generally. And people, even though people are providers of sparks, people are also very good at putting out fires. And so the relationship between drought and area burn just isn't as clear once you step outside of forests. And so forested areas are where we see the strongest climate change effect on fire. But this plot still says that outside of forests, if we warm and dry the environment enough, as long as some other conditions are met, like there's enough fuels and there's a spark on just the wrong day, then we can still get big fires. But going back to forests now, you've probably all heard that fuel characteristics have changed a lot over the last century because we got so good at fighting fire. That's shown pretty dramatically here in this pair of repeat photographs, 110 years apart, both of the Yosemite Valley. And what we see here are two dramatically different ecosystems. My understanding is this is primarily because of us. Because we were fighting fires for so long, we transitioned to a forested meadow ecosystem where forest exists but in a patchier form to a heavily forested ecosystem. So it should be pretty intuitive if you give both of these ecosystems the same drought and then a spark on the same type of day, which one is going to produce the bigger fire. We know a lot about what was going on with forest fire or fire in general before we started keeping careful records. I showed you the tree ring examples, which are fascinating. Another pretty amazing thing that we humans do is we go and dig mud out of lakes in order to learn about past fire that way as well. In natural lakes, for many thousands of years when there have been fires, the ash and the soot settle into the lakes, settle down to the bottom of the lake bed, and then over the years get buried by new stuff and information from new fires. And so if we stick a tube down in the middle of the lake or into the bottom of the lake, pull it out, what we have is a sequence of mud that has variations in the amount of charcoal and fire soot. And we can read these sequences of mud in order to very clearly see periods of heavy fire activity and periods of weak fire activity going for thousands of years, not just the Western United States, but around the globe. Here is a record of lake mud charcoal going back for the last 1,500 years, and that's in red. This isn't just from one lake, this is from a bunch of lakes across the Western United States from a fascinating study that came out in 2012 that I didn't have anything to do with. What you can see is that there have been some centuries in the Western United States where fire activity was pretty light, and then there were some centuries where fire activity really picked up and stayed high for 1 or 2 centuries, a lot of variability. The dotted black line behind the red line is a reconstruction of drought from tree ring records. That drought reconstruction, when we compare it to the lake sediment core reconstruction of fire, tells us that the same thing that we're seeing today, drought promoting forest fire, has been going on for thousands of years. Periods of drought are times when fire activity was high. Wet periods were times when fire activity was low. And that was going on for 1,500 years in this record, and very, very likely many thousands of years before that. And then about 100 years ago, there's a huge divergence where the tree ring record says that if drought was still the main driver still the dominant driver of fire activity or variations in fire activity from year to year and decade to decade, then we would have expected fire activity to go up over the last century. But instead, in the late 1800s, early 1900s, fire was almost eliminated from Western United States forest ecosystems. The difference then between what we would expect fire to be, which is at the top of the plot, and where fire went, which is at the bottom of the plot, and this doesn't come up through present. The lake sediment core records don't have that type of temporal resolution, so this might take us up through the middle of the 1900s when we were still very much in control of Western United States fire. The difference between these two has been referred to as a fire deficit. There should have been fire, but there wasn't. And so stuff grew on the Western United States landscape that would have been periodically thinned out by fire. And so some of what's going on right now is probably that we're paying off the fire deficit. But how does that square with the argument I just made that warming and drying has been the primary driver of the increase in forest fire activity over the last few decades? Well, they're both going on at the same time. The data we have for the last 4 decades, the really precise data on area burned, and our precise data on climate tell us that over the last 4 decades, the relationship has been very tight. As the climate has warmed and dried, then fire activity has skyrocketed. But I'm arguing, and I think this isn't a new idea, this is common sense, that if we weren't paying off the fire deficit, if there was less vegetation to burn in our forested areas, then very likely this skyrocketing of fire activity that we've seen over the last 4 decades would not have been as extreme. Instead, we would have started at a baseline where there was more fire activity to begin with in the early 1980s when our satellite records begin, and we would have seen an increase from there, but we wouldn't have been starting from rock bottom, where there was essentially no forest fire, and now we're in a situation when we're constantly being surprised by just how huge and energetic these forest fires are. So 2 things are going on. We're paying off a fire deficit, and the climate is warming and drying, and these 2 things are interacting and causing a really big increase in forest fire activity. What else has been going on in the Western United States? Well, people have been moving here. Between 1990 and 2010, the population of the Western United States increased by 36%. And if you look specifically within the so-called wildland-urban interface, these are neighborhoods that are situated very close to dense and flammable fuels. Then the population in those areas increased during those 20 years by something like 55%. So disproportionately fast. So people have been moving in to flammable areas. People bring sparks with them by smoking or from equipment, from power lines. And so perhaps the increase in human population has also promoted the increase in fire activity. Well, what's really interesting is that even though the population is so much higher today than it was at the beginning of our satellite record of fire, there actually hasn't been an increase in the number of wildfires in the Western United States. We've seen somewhat of an increase in the number of forest fires, the annual frequency of forest fires, but we've seen a decrease in the frequency of fires outside of forests that compensates. And so if we add these 2 together, it's just a flat line. What this tells us is that it actually isn't the number of fires that's driven the increase in area burned in the Western United States. It's the size of the fires. The fires we're having today are able to get much larger than they were in the 1980s, even though there aren't more fires today than there were in the 1980s. These records I've been showing you go back to 1984 because that's when our satellite records begin, but there's a more comprehensive data set that gives us a reason or a cause of the fires that starts in 1992. And here now we can compare the records of fires set by lightning versus set by people or their infrastructure like power lines. And this is pretty interesting. Slight increases in the number of lightning fires. This isn't, I don't think, because lightning has actually become more common. I think instead it's because fuels are drier and so fires are able to escape our initial control a little more easily if they're set by lightning, which is generally further away from where people are living. But the fires set by people have actually become less common. One way or another, people are getting better at not lighting fires accidentally. You might think, okay, this is for the whole entire western US. California is kind of special in this regard. There's not a whole lot of lightning in California. All the big fires we hear about are set by people or power lines. But it actually is true in California. Even more dramatically so, if we look outside of forests, look at the plummet of the number of wildfires set by people. And so this is some good news. We are aware of the increasing fire danger, and we are being more careful. And there are other things going on societally as well. There are far fewer cigarette-lit ignitions today than there were in the 1980s through early 90s, partly because people are being more careful about fire, but also partly because smoking just isn't as common today. And so which fires are the ones that are growing the largest? Well, on average, all fires. The fires that humans ignite are getting bigger, but it's the fires that lightning ignites that is really dominating the record. Now, obviously, I'm not making an argument about the dominant cause of any one fire. We all can think off the top of our heads of a catastrophic fire that was set by humans that was probably bigger because of climate change than it would have been otherwise. But if we want to understand the story of the entire Western United States, it's lightning-ignited fires that are really driving the big increase in annual area burned. And very likely one of the reasons for that is just because people are so good at putting out fires, but they're best at putting out fires close to where they live. Lightning tends to occur in remote mountains, in rugged places that are heavily vegetated, and therefore places where a small fire is very likely to be able to become a big fire before people can get there to address it. So what do we expect for the future? Well, here's that vapor pressure deficit variable on the left. What's happened over the last century is in black, and so you can see that it's increased over the last century because the atmosphere has warmed. And then the colored lines are showing us what climate models project should occur because of because of greenhouse gas emissions into the atmosphere. This isn't just one climate model. This is the average, or this is the information accumulated from 34 different climate models. Some models are better than others at some things versus others, and so we, climate scientists, when we have the option, we like to take the information from a bunch of climate models and average them together. The first thing to note is that the rate of increase in this vapor pressure deficit, the sponginess variable that we've observed in the real world, is actually pretty well in line with what climate models say should have occurred because of greenhouse gas warming. Which is to say that if we hadn't warmed the atmosphere with greenhouse gases, we probably wouldn't have seen an increase like this in the vapor pressure deficit. The second thing to note is that when these climate models are run out into the future, by the 2050s to 2070s, depending on how much greenhouse gases we put into the atmosphere, the average year is projected to have a vapor pressure deficit value as high as the ones that occurred in 2020 and 2021 when the forest fire activity in the Western United States shattered the old records. But vapor pressure deficit is not the only thing that matters for fire. There are many climate variables that matter for fire, but the other obvious one is precipitation. And correlation studies say that probably the most important precipitation variable is how frequently it rains during the summertime. How much it rains is also important, but actually the length of the dry periods between the rains is really important. And with that one, it's a lot harder to tell what has been due to climate change versus natural bad luck. Our records are shorter. The black one is an observed record. It goes back, in this case, to about 1950. And you can see there's been a big decrease just since the 1980s, but that may have just been a return to a normal level from the middle of the century. What do climate models say should occur because of human-caused climate change? Climate models tend to say that we should expect future summers to have fewer rainy days than historically. By the middle of this century, they, on average, project that there should be an 85% increase in the frequency of, this is complicated to say. There should be an 85% increase in the frequency of years with very few rainy days. So more years with not many rainy days. There will still be plenty of wet years. And this is important to keep in mind. In a warmer world, there's actually more precipitation than a drier world. A warmer world has more evaporation off the oceans, and so there's more water falling out of the sky in a warmer world than a cooler world, but that doesn't mean it's going to get wetter everywhere. In summertime, if you look at a map of projections of precipitation across North America, California especially stands out as a place where the models say drying during the summertime. So these plots suggest to us that we should expect continued increases in wildfire activity in the western United States, especially in forested areas, because fuel is not so limiting in those areas as outside of forested areas. And remember the exponential relationship between drying and fire. If that relationship continues, then we expect that burned areas will continue setting new dramatic records. But the future is going to be a lot more complicated than that because fire affects fuels. Here's a picture from 1989 in Yellowstone after the big fires that occurred in 1988. And you can imagine that as we warm the planet, the areas that didn't burn, fire might behave differently. Future fire might behave differently in the warmer world in the areas that didn't burn versus the areas that did. And so as these fires are growing in size so dramatically, then at some point fire should start becoming self-regulating. And here in Santa Barbara, we're familiar with this. If you go to any place that burned in the last 5 to 10 years, for example, you can imagine that fire behavior in that specific place is going to be different for the next several years to decades until fuels reaccumulate. And this stuff is really complicated. Every ecosystem is different. Trying to predict the species that comes back after this giant fire in 1988 in Yellowstone, for example, and trying to predict how many of these trees are going to survive and how big are they going to get. When does the potential for large forest fire in Yellowstone return to the 1988 levels? This stuff is very difficult to predict and it requires expertise from a huge range of people. And so here's the group that I've been working with to try and answer this question. And the project that we've been doing is to create a computer model that can simulate not only fire, but the way that fire interacts with forest ecosystems. So we're trying to create a model that is growing forests inside the computer. And then climate is occurring on top of those forests, and fire is occurring in those forests. Fire burns the forests, and then the computer grows new forests based on what computer seeds were growing in the computer soil. And so our team includes forestry experts, computer experts, modeling experts, and grad students who are just getting started, including Melissa, who's here today. She's in her 4th week of being in grad school, and this is a project that she'll be helping with for the next 5 years. And so our computer model, we've built this forest ecosystem model, and it does things like simulate the amount of carbon stored in live leaves and branches and stems, and it's also keeping track of dead fuels. And when fire occurs, the live stuff turns to dead stuff, and then the dead stuff decomposes. It keeps track of how big the trees are in width, how tall they are, how dense they are, and all of these variables are important to our fire modeling. All these variables affect the way that fire works. And so our fire model uses variables such as tree density and the annual cycle of lightning frequency and anomalies of the vapor pressure deficit to not just model how much area should burn in a given year for the entire western US, but in any individual location. Because if we want to understand the future of fire, in order to actually be able to do something, if there's a place that we really don't want to burn catastrophically, and we think that maybe we want to thin fuels in order to prevent the catastrophic fire, then we need to be able to put some numbers on the probability that this treatment that we want to do is actually going to work. And a computer model could be the way to do this. And so what I'm showing you now is really exciting. This is the results of a simulation that I ran yesterday using the new model that I fit the day before yesterday. So this is all new stuff. And what we're looking at here is the monthly probability of fire mapped across the western U.S. In the spring, the fire season begins in the southwest, and then moves to the northwest and away from the southwest during the monsoon. And we can't just run our model one time. We need to run it many times because fire is a chaotic thing. The real world has only had one chance to do its real world thing, but in the model world, we can run the model, in this case, 500 times, and this takes about 3 minutes. And we can track with every single model realization, shown in gray, the possibilities that could have occurred over the last 40 years. And the average of all those 500 possibilities is shown in the dark black. Well, how does this compare to the real world data? If we force the model with real world climate data as observed, our model actually does really well. Here is the long-term average of fire potential forest fire potential on the left axis, and the average of all of our simulations. The total annual forest area burned is in black, and then red is the observed record. And so we are capturing the vast majority of the year-to-year variability in the real-world fire, as well as the majority of the trend. We capture about 70% of the trend, meaning that this trend toward increases in forest fire, 70% of that trend is accounted for by our model. Model does pretty well spatially. You can see that if I just split the western United States into 4 different regions, it does pretty well in each. As you zoom into a more granular detail in any individual location, it becomes harder and harder to simulate what occurred in the real world because fire is probabilistic. There's nowhere on the planet that we know of that has a 100% chance of burning next week. But you can see that these 4 records for these 4 different regions look quite different, and the model is able to capture those differences. Our computer model is doing okay at simulating the annual cycle of fire, but there's definitely a room for improvement. I show this to you to show you really why you haven't heard about this model until today probably. We'll be hearing about it next year probably after some more work. But I think it's still pretty impressive that in the Four Corners area, we can tell that the annual cycle of fire should look much different than the Pacific Northwest, for example. And so then we can use this model to address a simple question. What if these trends from greenhouse gas emissions had never occurred? What would fire have done over the last 40 years? Assuming everything else stayed the same, assuming that we still went into the 1980s with artificially dense forests because of fire suppression. Well, all we have to do is run our model simulation after subtracting away these human-caused climate trends toward warming and trends toward some reduction in the number of rainy days per summer. And that's what's shown in blue. And so if you compare the black, those are our original simulations, to blue, the new simulations in this hypothetical world where climate change never occurred, you can see that by removing the climate change trends, we remove all of the increase in forest fire activity. But that answer isn't the same everywhere. This is now a map of the effect of climate change on forest fire in the western United States. You can see that in some areas the effect of climate change has probably been very potent. In other areas it hasn't been. And the big variable that explains the differences you see in the map between the whiter areas and the redder areas is fuel. The places with more fuel, the effect of climate change has been able to be more potent. Places with less fuel, it takes more than just a warm atmosphere to carry a big fire. And so it's harder to detect a climate change signal in those areas after just 40 years. What does all this mean? I said earlier that because of this exponential relationship and our expectation that drying is going to continue leading to big forest fires, I said that we might expect that fire starts becoming self-regulating. It starts becoming hard to have big fire years because we've burnt so much forest in the last few decades. But we're nowhere close to getting to that point. Of course, there are individual places where we wouldn't expect a big forest fire to occur in the next couple decades because there was just a big forest fire in the last few years. But in the last 40 years, even though it seems like we've had so much forest fire, not even 20% of the forested area in the western United States is burned. That means on average, over the last 40 years, we've established a fire return interval of something like 200 years. If you only burn 20% in 40 years, that's not very much forest fire. The vast majority of forest in the Western United States is still waiting around to burn in this artificially warm world. And so I haven't run yet. In the next couple of months, we'll run model simulations into the future. But my prediction is that it's going to take a while for the model to say that fire should start becoming self-regulating. So it's going to take a while before we see this rapid increase in forest fire activity start to level out. Okay, so this may have been very unsatisfying for those of you who do so much thinking about this local area. This local area is not heavily forested, for example. And so what's going on locally? Well, here's the area burned record for Santa Barbara County and Ventura County. Most of the talk today was about Santa Barbara County, but as I said earlier, with studies like these, it's helpful to zoom out as much as possible. So this is about as fine scale as somebody like me ever looks. And what you can see is that the burned area record here is basically binary. It's either a big year or it's not a big year. And it looks like there have been more big years in the last 20 years than the 20 years before that. And if I extended this plot out to the early 1970s, then we generally see the same thing. And so maybe there's a trend toward more fire. But it's really tough to tell, actually. This trend is not statistically significant, meaning that trends like this, clusters of big fire years, can occur just by random chance. So am I saying that climate change isn't affecting fire in this area? No, not at all. It makes perfect sense that if you warm up the atmosphere and dry it out, then the potential for big fires grows. But in an area like this, where fuels aren't nearly as dense and not nearly as continuous, then it takes a lot more than just warming and drying the atmosphere to get big fire. And so it's probably going to take longer before we really see a statistically significant trend emerge. The fire regime here on this part of the coast is really complicated and actually quite different from the forest fire regime I was talking about earlier. The forest fires I was talking about earlier are really dominated by the summer season. The histogram here is showing the percent of area that burns that's burned in these two counties by each of the 12 months. And what we see here is that there is quite a bit of fire in the summertime, but there's also a ton of fire in the fall. And these fires in the fall require a lot more than just a warm atmosphere. They generally require really strong winds to occur. In this area, generally you don't get Santa Ana winds, but you get these really strong sundowner winds. But a big sundowner event isn't going to really promote a big fire unless the first rains of the fall and winter haven't come yet. And so there's a lot of other stuff that needs to occur in order to set the table for climate change to then be able to drive a big fire here in Santa Barbara. In addition, a ton of the area has already burned sometime in the last 40 years. And so fuels have been affected by by fire here. And so it's very, very complicated outside of forests, or even more complicated outside of forests, to know how are fuels going to respond to fire. The last 20 years have been really dry, and so post-fire, a lot of ecosystems, a lot of vegetation ecosystems haven't rebounded back and become flammable really quickly. We also have a really consistent marine layer here during the summertime. The strength of the marine layer and the amount of cloud shading correlates with fire activity. And so as we move into the future in a warmer world, the dice in this region are very likely loaded toward bigger fires. But it's pretty impressive to me that we have a community that is so dedicated now to making themselves resilient, even though the evidence that climate change is already causing fires to every year just be more and more out of control in this area isn't all that clear. Instead, this community is using logic and saying, when the atmosphere warms and dries, then stuff is going to get more flammable. And so then if all the other requirements of fire are met, then we're very likely going to have bigger fires than we've ever seen before. So it's pretty inspiring today to hear about all the plans that are going into this. And the last thing I'll say is that this talk was about area burned, because that's a really easy variable to measure and talk about, but it's not the whole story. Some of the most catastrophic fires that have occurred here haven't been the biggest ones. The Tea Fire, for example, that was 2008, I think, and burned more than 200 homes. It wasn't a huge fire, but it was in a really bad place. And so I don't mean to say that the only thing we care about is big fires, but it is a variable that's easier to understand. And as fires are getting larger, they have been getting more severe as well across the western United States. With that, I will wrap up and be happy to take some questions.
Do we have some questions for Mark?
So you sort of touched on it on the end. I was very interested in what's different about Santa Barbara versus the much bigger western region. So the big difference here is we don't have forests for the most part, but we have lots and lots of chaparral. And so, but is it still true, because everything else you're talking about, it's really the increase in fuels. So is that still true in a chaparral, just as true in a chaparral?
Well, there are probably 10 people in the room who know more about chaparral than I do, and so I'll go superficial, and then I'll let somebody else, like Dar, answer if he wants. I told Dar before this talk that I expected this exact question, and hoped that he might be able to help a bit. So chaparral is not. Chaparral is very dense. It burns very easily. The chaparral fires on the Central Coast, and I'll lump this area into that, are driven. These are generally wind-driven fires, and they're generally not occurring during the summertime. So for some reason, it's different from the summertime forest fires that are occurring specifically during the dry season and are getting reliably bigger every year. And I don't know if it's because chaparral also requires continuity of grasses between chaparral areas to really create big fires, and therefore a really reliable response to climate change that we can see on the scale of a few decades. But the fires that we do see dominating the chaparral ecosystem here seem to require these really strong winds that are occurring more often than not in the fall, and those winds can only cause a big fire if you've also had the bad luck of having the rainy season not start yet. And so those fires have gotten bigger, it seems, but something is different. Dar, do you would like to say anything else about chaparral?
There is a sort of condition under which things like chaparral make these really big fires, and actually Max Moritz and others have done work on that. It's sort of like 60% live fuel moisture is considered to be this critical threshold where very, very large fires can occur. But recent work has actually shown that number can actually be also 75%. So there's actually slightly wetter fuels that can produce these very large fires. And so, you know.
Can you use the mic? Yeah, we can't hear you.
Okay.
So 60%, there is a fuels component which is tied to live fuel moisture. So at a certain critical live fuel moisture level of 60%, you can get these very, very big fires. And some recent work by Max and others have found that there's another threshold where you still get big fires, and that's the 75% threshold. So weather is a major control, but overlaying on top of that, with these winds, overlaying on top of that is things like drought and also amounts of fuels and frequency. So it is mostly weather, but also drought plays a huge role in some of these really big fires in California, in shrublands.
So could you review the components that make up a red flag alert?
It's generally, I can't give you the exact numbers, but I think Rob Hazard or others could. It's basically high winds, high temperatures, low humidity. And the red flag, it's beyond a certain wind speed, and I think it's actually mostly by humidity deficits and temperatures that are the red flags.
I also wanted to add that I remember reading in regards to chaparral fires that with climate change there is likely an increase in precipitation variability in this region. which would increase the chances of kind of whiplash years. So really wet years followed by really dry years, and that increasing vapor pressure deficit. And so that wet year can create an abundance of fuels, especially grass, that could carry large fires in between mosaics of chaparral, which would then lead to the increased frequency of large chaparral fires.
Hi. I was wondering if you're working with the Forest Service or something to figure out like what controlled burns would do to your models.
No, not yet. Right now, we're doing all the computer work to try and get the model to look to a satisfying degree enough like the real world. And then what you're suggesting is exactly what I want. I actually don't have any collaborations at the moment with the Forest Service, but I have been talking with some folks at CAL FIRE. CAL FIRE has a research division, and they know about our modeling. And they've basically told me that when I'm ready, they want to talk so that they can learn and give input to help the model be better. What you're saying about controlled burns, though, is right on and a great idea. One of the uses of the model is to use it to explore the potential for expensive or risky management strategies to actually work. And one thing right now that is seen that is very expensive and seen as very risky are large controlled burns. Or controlled burns generally really small. And if we want to actually help wildfire along in addressing the fire deficit, then very, very likely it seems that we need to be lighting bigger fires. And so hopefully we could use this model to be able to understand the effectiveness of prescribed burns.
So Park, I was interested in the data that you showed showing ignitions in Southern California have declined even though populations increased. And I was wondering if there was a spatial pattern to ignitions. Are there more ignitions in wildlands, in the WUI, or in the urban areas? Because there is a geographical kind of hump-shaped relationship there.
Yeah, I wish I had the answer for you without needing to go to my computer, but I don't. There's definitely some geographic variation, or a lot of geographic variation for sure. The plot that I was showing you actually was just looking at fires that grow to 250 acres or bigger. And so we don't have 250 acre fires in the middle of LA. You have to go out to where there's actually extensive areas to burn to get a fire that size. I think that Rob Hazard may have had a comment.
Just in general, in Santa Barbara County, I assume it's the same for Ventura, and then pretty much across Southern California, vast majority of ignitions are along roadways or power line corridors. Some associated with recreation, campgrounds, things like that, trails. Very few ignitions out into wilderness areas. We get lightning complex fires here in Santa Barbara County, but they're few and far between. When they happen, you're spot on. They tend to be tough to deal with because they're out in the middle of nowhere and it takes time to get to them. That's just looking at ignitions. Every year in Santa Barbara County, we probably average about 80 to 100 ignitions. But those that actually turn into a fire is more cyclical based on fire return intervals, seems to be the biggest precursor to large fires when you combine that with the weather elements that you're talking about. The wind events, or middle of summer. So folks in here that remember the Zaka fire, that was a midsummer fire in the backcountry, more fuels dominated versus Thomas fire, late fall, early winter, wind-driven fire.
And I was going to ask you,
Oh, sorry.
I can't tell who else has the microphone. In our front country more, we have primarily oak trees, right? And then when you get way back, big pine, little pine, and that will have pine trees which are more similar to Montana, Idaho, Washington State kind of timber, that once that burns, it seems to me why I don't want to buy a cabin in Montana anymore, is once that burns in my lifetime, those trees around that cabin are never going to look the same. I wouldn't have the same shade or anything. But the difference being, does it make a difference on the grow back? Because our oaks grow back, and then they create that shade for the undergrowth. So can you kind of speak to the differences in those types of fuel?
Boy, probably not very satisfactorily. No, I'm sorry. I think that I think that I think it's above my pay grade. I'm just not an expert in the succession of vegetation ecosystems. But I've yeah. If Frank wanted to say something. No, let's not put. So I don't mean to put anybody on the spot, but yeah, I'm sorry. I just don't know I don't know enough to embarrass myself further.
Well, I'll just say quickly, I think one thing that will distinguish, the oaks here are very fire tolerant, and the live oaks on the Santa Barbara side often resprout quite vigorously after a fire, so their recovery is fairly quick. The conifers, the big conifers can resist fire. They can survive a lot of fires until they're too severe, but they don't have that same kind of resprouting and rapid growth if the mature tree's been killed. They have to start from seedlings. So that's a big difference in the kind of recovery and the recovery rate of the oaks compared to the conifers.
Like I said 15 minutes ago or so, this stuff takes a big team. You need to have a whole bunch of different expertises.
I was going to ask you a question about the way that you parameterized your model at the beginning in terms of the vegetation. Like, it seems like that would have a big effect on the way the model runs. And so do you have vegetation structure in there, or what gives you your starting value in how you run those models?
Our forest model, which we just published, is created by my collaborator, Winslow Hansen. And I think that he is mostly starting, so he does a 300-year spin-up run, but he starts the forest model with we have 12 different forest types in the model, and those forest types are are placed in the model where we know they are today. So in this way, we're cheating. We don't know exactly which species were distributed where at this fine of a spatial scale, which is 12 kilometers. Or no, our forest model works at 1 kilometer. And so I believe that Winslow is just starting the model with forest species as they are today, but then runs for 1,200 years, and the distribution of forests are allowed to change during the model spin-up time as a result of fire, climate, and randomness.
Okay, and then I was going to also ask about this summer, late summer. We had a lot more humidity here than we've had before, and it got me reading about the monsoons and how the monsoon patterns might change and fog patterns might change. And you know, your story you told us was kind of depressing about vapor pressure deficit constantly increasing and stuff. But I'm wondering if these other changes are being modeled as well and considered like that. There could be changes in humidity that would keep the vapor pressure deficit from rising as much as we're seeing.
Yeah, and you actually see this in the model projections for coastal Southern California. The average of the 30 or 40 models shows an actual increase in relative humidity during summertime. And it's tough, like right on the coast. It's tough to trust these something that spatially nuanced as increased relative humidity right off the coast, because the models are modeling slight increase in relative humidity over the ocean. Models don't have very fine spatial detail, and so how much of that is actually going to occur over the land versus how much of that is just the model splitting some land and some ocean over the same model grid cell. But locally here in Southern California, it's certainly not all certain. We hear a lot about how precipitation is going to decline because the models say that from about Los Angeles south through northern Mexico, fall and spring precipitation decline in the future. If we look to see what's actually happened in the real world, there's not such a detectable trend here in California. We hear also, or Southern California, we hear about how fall precipitation is projected to set in later in the year, loading the dice for more fall fires driven by Santa Ana winds. But there's not a detectable trend in the timing of the onset of the fall-winter precipitation season yet. We hear a lot about how Santa Ana winds might become more energetic in a warmer world, but actually we might expect the opposite. Santa Ana winds are promoted by a cold continent and warm ocean, and global warming actually does the opposite to the continent ocean temperature contrast. If we look to see what's happened in the real world, there hasn't been a trend in the frequency or intensity of Santa Ana winds. So here in Southern California, there are a lot of other things that might be going on, there are a lot of other things that might not have. What am I trying to say? Fire, you need a lot for a fire to occur here in coastal Southern California, and not all of those are influenced in a bad way by human-caused climate change. Whereas you go to a dense forest in the Sierra Nevada, and it's just a lot more clear that the dice are increasingly loaded toward big fires in those areas. It's hard to find one variable that is supposed to trend in a direction that would actually reduce fire risk.
All right. Hi. Just a quick question. So in your model, you were showing us that if you remove the human influence, then you remove the whole trend, right, of fire probability.
What kind of influence?
In your model, you were showing us that if you remove the human influence in the simulation, you basically would remove the whole upward trends. But my question is, so that human influence comes from carbon emissions and greenhouse gases emissions, that's how human influence should be read, that like you don't have, for example, like population or other type of human feedback that it's beyond, carbon emissions.
Yeah, so this question is about the two model simulations. One where we simulate the fire in response to climate as it was observed, and another where we simulate fire in response to this hypothetical world climate where the climate change trends never occurred. But everything else stays the same. So the model knows about changes in human population. The model knows, we don't go into the future, so we're just looking at the historical period. The model knows that human population increased by 36% between 1990 and 2010. The model knows that forests are being influenced by a trend toward drought and a trend toward fire in the control run, but not in the no climate change scenario. So yeah, it's pretty complex.
I think we have time for one or two more questions. I know there's one hand up here. We do have a reception out there, and Marie probably has an announcement she wants to make. So, but let's have a question.
Okay, I just wonder, have you studied or have you noticed a trend in
monsoon activity from Mexico and dry lightning happening? Is that increasing or will?
So many of these questions are so great for other people in the crowd. I know something about this. The models, I believe, project a intensified monsoon, but also more variable, I think, in the Southwest. Do you know if that's right? Okay. Layla says that's right. I reviewed one paper about how models simulate the southwestern monsoon, though, a few years ago, and learned that most of them, or maybe none of them, actually simulate it correctly. They don't have moisture coming off of the Gulf of California, for example, as much as occurs in the real world. And so I'm pretty skeptical about anything models have to say about what to expect of the intensity of the Southwest U.S. / Mexico monsoon. Dry lightning, though, I'm just going to go on a limb here, and Layla can correct me if she knows that I'm wrong. I expect that dry lightning would be more common in a warmer world. There's more water vapor in the air. There's more energy for convection, but the air is also warmer and more arid beneath the clouds, and so more often in a warmer world, I think you can have a monsoon storm that actually doesn't hit the ground, but you can still have the lightning associated with the convection. Layla nods like that sounds reasonable. Just, let's keep it to one.
So I had two questions. They might both be unfair, so apologies. But so the first one is about this anthropogenic versus non-anthropogenic simulations and these scenarios. Do you have any idea about what the contribution is between anthropogenic climate versus like the naturally occurring mega drought that we're in just now? If you can separate those effects. And then the second part is there any contribution from bark beetle and tree death to burned area?
Great. Okay, I'll take both. They're both fair questions. I'm the person who did the mega drought study that you're referring to, where the contribution from human-caused climate change versus natural variability was parsed out. We found that the last 22 years, very likely, if you look across Western North America, been the driest 22 years since our triggering records began in the year 800, so in the last 1,200 years. We then do some modeling, and our best estimate is that 40% of the severity of this drought was due to the background warming trends caused by human-caused greenhouse gas emissions. And it's that 40% that caused what would be a serious drought to instead be a record-breaking drought on this 1,000-year timescale. But it would be a serious drought even without human-caused climate change from a soil moisture perspective, and that's because, very likely, precipitation has been lower than average over the last 22 years. We've had, in the last 22 years, I think 4 years have been wetter than average, and the other 18 have been drier than average. There are only 2 other 22-year periods in the last 1,200 years that have that concentration of dry years, and a good amount of that is due to reduced precipitation. Climate models, if you ask a climate model how precipitation in the Western United States responds to human-caused greenhouse gas emissions, they're actually all over the place. Some say it should get wetter, some say it should get drier. If you average them all out, then it says basically nothing. If you look at what's happened in the real world, there's been no trend in precipitation. It's just been dry in the last 22 years, but that's not on the end of a big, long trend. And so our best guess right now is that this drought, from a precipitation perspective, is pretty much naturally caused, and across the Southwest at least, that makes sense. A lot of the last 2 decades have been in a La Nina sea surface temperature state in the tropical Pacific, which we know affects or loads the ice toward dry years in the Southwest U.S. and northern Mexico. About bark beetles, this is really complicated. It makes perfect sense logically, I think, that if you kill a huge patch of forest with bark beetles, then that wood would be more flammable than it would be if it was alive and still pulling moisture out of the soils. And maybe someday that will be borne out in the actual data, but the studies I know about where scientists go and look to see whether or not the fires are occurring more in bark beetle killed areas than outside the bark beetle killed areas, the data actually don't support that yet. And maybe it's because it's more complicated. Some scientists say that right after bark beetle kill, when the trees are in the so-called red phase, when dead needles are still on the trees, then fire risk is really high, but when the needles drop on the ground, then fire risk goes down because the atmosphere can circulate differently through that needleless forest that's in the so-called gray phase. So I'll leave it at there, and when the real experts in the back of the room want to teach me something out over during happy hour, I'll be happy to listen. Thank you.
Thank you.
I just want to thank Park for coming, and thank you all for being so concerned about wildfire. You came out here on a Friday evening. Before you wrap up, I just want to say a few things. If you guys would like to learn more about wildfire, Fire Council is hosting a big community event tomorrow here again, 11 to 5. We'll have booths from local organizations, fire trucks, county helicopters coming again. We'll have a speaker from the Department of Insurance to learn about Fireways USA and how to make your community more resilient to wildfire, and also learn about evacuation preparedness. We have a nice spread of food outside from a local caterer and from a local UCSB employee who wanted to feed you all. We have wine donated from Demetria Winery, which is a very nice winery, so go test that out, and some more wine from UCSB. And a local agave company came, and they have this really cool connection between economic solutions to wildfire preparedness and resilience. So go test out their samples and chat with them about that. And thank you all for coming, and Park will be here for more questions. Thank you, everyone.